Hello, welcome to our next set of stats notes. We're working on section 4.1, so we're moving into chapter 4. Chapter 4, we're going to deal with probability. A lot of times when we're working with statistics, we're going to be taking just samples out of the big whole set of data. And when we do that, we're going to use some random chance to make those choices to pick our sets of data. So there's going to be a lot of probability aspects to what we're doing because there's going to be chances of picking a good sample, chances of picking a bad sample, all that kind of thing. So we're going to spend a lot of time finding out how to calculate the chances and probabilities in this next chapter, just so we can get an understanding of probability so we're ready to use it in later sections. So for this first section, we're really just going to introduce the idea of probability and how probability works. First off, there are a couple different ways to think about probability. The first one is relative frequency approximation. This is also called experimental probability. This is where you go out and you do an experiment and you collect the results, and then you use that to find the probability. So we do an experiment. So like when you roll a die or draw cards from a deck, if you actually sit there and actually do it, and then we calculate the probability, we look for the number of good results, what you're looking for. So if I'm rolling a die and trying to get a 4, every time it comes a 4, that would be a good result. And we compare that to the total number of tries. So if I sit there and I roll the die, 100 times and 40 times it comes up as a 4, then I'd say I have, 40% chance of it coming up a 4, because 40 out of 100 is like 40%. So we look at the number of good results compared to the number of tries. Compared to number of trials, I should say. Number of trials. So that's relative frequency approximation or experimental probability. This is actually something we actually deal with a lot in statistics, because a lot of times statistics, the best we can do is take samples and look at the results from the samples, and that's kind of running an experiment. We're actually sitting there and doing a survey or whatever to collect data from a group, from a larger group, and then taking that to figure out what the probability is of a certain people being in a certain group. If you want to do a study on number of people that have, or percentage of people that have college degrees, you'd sample the whatever nation or state or whatever you're in, and then you look at your sample, how many of them do have college degrees out of the number you sampled, and that would be your probability. Now, the one that's probably a little easier to calculate, and so we'll probably focus it more on it in this chapter just because the calculations are a little more straightforward. You also don't have to actually do a bunch of experiments. That's the classical approach. That's probably what most people think of when they think of probability, also called the theoretical approach. This is where you say what should happen based on knowing what's going on. Like I know a 6-sided die has 6 sides, right? And I know that only one of them is a 4. So I know that 1 out of every 6 rolls should be a 4, because there's only 1 4 out of those 6 sides of the die. That's the classical or theoretical approach. So this is what should happen. So what should happen? And to calculate this, we look at the number of good options. If I'm looking for a 4, there's only one option, but maybe you're looking for an even, and then there's 2, 4, and 6 would all be good. So you can sometimes have more than one good option. So you look at the number of good options versus the total possible number of options. So on that die, we said there's 6 different ways you can get numbers you can get on a 6-sided die. So that would be the total options versus total number of options. So that's the theoretical or classical approach, where you look at the what should happen. You think, okay, how many possible good results are there versus how many total possible results are there? Okay, the last one is subjective probability. This one's not something that, is super rigorous. We have a lot of mathematics to do, but it's one we use all the time. It's what you think about what should happen, based on your experience, kind of your idea, observations you've had in the past. You just think, okay, what should, what do I think will happen? So this is just based on past experience and observations. This is when I'm trying to think about which gas station I should go pump my gas at, and I know that in the past, my experience, the gas station closer to home is a little more expensive than the one that's like a little bit further away. So I tend to go to the one that's further away because I tend to expect to get cheaper gas. That's, I'm not doing any actual calculations or computations to figure that out, but based on my experience and my observations, I kind of think, okay, from what I've seen, typically that gas station is cheaper. I'll go to that gas station. Or if you're, getting ready to do homework, you kind of have an idea about how long your homework will take. Oh, I've done a few assignments now, and so I kind of expect, okay, the homework's going to take about this long, and that's based on your experience, your observations. So based on past experience and observations, it's subjective. It's not something strictly really calculated. You're usually not going to have a good number, like say exact, but you're going to have kind of an idea about what to expect. So subjective. We use it all the time, but it's not something we're going to spend a lot of time calculating because it's more of a, in my experience is what I expect. Okay, we're going to use the classical approach. Again, like I said, classical approach is kind of the one that's the easiest to calculate. You don't have to do an experiment. You can actually work with real numbers. So that's the one we'll probably work with the most. If I roll a 6-sided die, what is probably the roll of 3? We're going to write this both as a fraction, a decimal, and as a percent, just to show you that you can have all three. You'll see a lot in statistics as we move forward. A lot of times we'll have decimals given to us that are probabilities, and so we'll see a lot of decimal probabilities, so you got to watch out for that. Fractions are nice. They're a great way to represent probabilities, but you can always turn those into a decimal. And then percent, out of 100, we can think about probabilities at 50% of the time something happens. So you'll see all three used, but watch out for a lot of decimals. We'll see those in the future. Okay, so we say 6-sided die. So we have 6 total possible options, right? We always put the total number of possible options on the bottom. Since it's a 6-sided die, there's 6 options. And what is the probability of a roll of 3? Well, there's only one 3 on a 6-sided die, right? It's just 1, 2, 3, 4, 5, and 6. There's only one of those, so it doesn't matter that the number's a 3. I'm thinking about how many options are there that are a 3, and there's only one. If you're looking at the good options, well, there's only one 3 on that die, so 1/6 is the probability for that, because we're looking at, okay, there's one side that's a 3, one side that's a 3 out of the 6 sides of the die. And of course, we want to turn that into a decimal or a fraction, so we'll take 1 divided by 6 and get our decimal. So that's like having 0.16 repeating. Calculate around to 7, but it means 0.6 repeating. They just rounded. And then you can turn this to a percent too. Remember to take decimals to a percent, you just move the decimal over 2 spots. So this would be like 16.7%. And if you're ever doing a decimal for a probability, my stat lab will tell you what to round to. I just rounded it to 1 decimal place. So like I took the decimal here and moved it over 2 spots, and I got 16.6 repeating. And so then I just round that up to a 16.7. So that would be the fraction, decimal, and percent versions. And they'll tell you what to round to and stuff like that. All right, let's do one more. Okay, we have the same 6-sided die, but now I'm looking for the probability of rolling an even. Of course, evens means that 2, 4, and 6 are all good options now. So when I go look at my good options, results that I want, there's actually 3 of them, right? That's funny, we're using 3 the first one, we only got 1, but that's because there's only 1 3. Now we're looking for evens, and there are 3 evens on this 6-sided die. So there's 3 good options. Again, the total, it's the same die, right? Same 6-sided die. There's 6 options. So we have 3 6. Now, be careful. You should never leave a fraction unsimplified. So if you put 3 6 in my stat lab, it's going to tell you that's the right answer, but it's not simplified. So always make sure you simplify your fractions. 3 and 6 both divide by 3, so you get 1/2. So 1/2 is the fraction they're looking for. If you divide 1 by 2, you get 0.5. So 0.5 would be the decimal version. And then 0.5 or 1/2, that is 50%. So that is 50% for the percent version. So if I say the chances of something happening are 1/2, 1 and 2, 0.5, or 50%, that's all the same thing. All different ways of saying, the probability of that happening is 1 and 2, 50%. 50% of the time it's going to happen. Half the time it will, half the time it won't. So that's the basic idea. Now, when you're working with probabilities, you're going to have to sometimes work with charts where they give you data and put that data together to get your probability. So this chart shows the number of rooms and houses for sale on a popular real estate website. We want to find the probability the random chosen house will be less than 5 rooms. So less than 5 means I'm looking for these numbers. So these numbers up here, that's going to be my group that's less than 5. So that's what I want to be less than 5, right? I'm not including 5 because that's equal to, not less than. So if I want to find the number of good options, well, in this case, I actually have to total this up myself. I have to take all these options and add them together so I can figure out how many good options there are. So I'm going to do that. Take these numbers, 670, 12, 1325, 10, 999, oh, I missed the 0. Okay, 10,989 and 23,265. And this will give us the total number of good options. So because these are the number of different houses, and those are the number of houses that have less than 5 rooms. So the good options is 36,259 over total. Well, total, I'm just going to have to add them all up, right? So I'll take those ones I added so far, add the rest. So I'm going to add in the 27,901, I'm going to add in the 24,624, add the 14,676. I'm going to add the 17,230. Okay, I hope I got those all typed in right. That's always good. You've got to be careful, make sure you're typing things in good. And I get a total of 120,690. Now, something like this is not going to come out as it's probably a little bit harder to simplify. You can make your calculator sometimes simplify fractions like this. So if you type it in as a fraction by doing 36,259 divided by 120,690, so I just use the divide by button, this division button, to get that fraction there. And then you can get it into a decimal. So if you want the decimal, if that's what my stat lab wants, or you have multiple choice and you can find the decimal, that's fine. But if you want to turn it into a fraction, the math button will let you turn it into a fraction because the first option is fraction. You just hit enter twice and take that and turn it into a fraction. Now this is where the problem is. Sometimes when fractions are this big, it will not do that. If the fraction was a little bit smaller, if I had smaller numbers, it would actually take a fraction and simplify it. Like if you type something like 6/8 and then hit the math button, it would actually simplify it down to 3/4 for you. So it'll simplify small fractions, but big ones like this, it's not going to. So that one, you're probably going to stuck the answer with a decimal or leaving it as like this. You could maybe look for things that you could divide the top and the bottom by if you really want to try and simplify it, but something like that I'm not going to be really worried about. Like, on the tests and stuff, you'll get the decimal is what they'll probably ask for and something like that. All right. Let's try one more. So below it listed all possible combinations for rolling 2 dice. So here we're rolling 2 dice at the same time. Find the probability of both dice being odd. So if I want both dice to be odd, so again, I'm going to look for the number of good options. Thankfully, they kind of give us a little chart here. So instead of me having to just figure it out in my head, I can just look for the pairs that are both odd. Like 1-1 is both odd, 3-1 is both odd, 5-1 is both odd, 1-3, 3-3, 5-3, 1-5, 3-5, and 5-5. So those are all my good odds. None of these twos have, these are all 2, 4, 6, so they don't work. There's 2, 4, 6, those don't work. So just these 9 of them are good options. Total number of options, since I had 6 by 6, there are 36 total number of options. So that would be my probability for this one. Again, this one is smaller, this one would simplify. So this is one where I pull up the calculator, 9 divided by 36. And that would simplify to 1/4. So this one does simplify to 1/4. So it's nice. You don't have to really worry about simplifying yourself. You can always make your calculator simplify these using that math button and the fraction option. So that would be 1/4. So 1 odd over V4 is going to be is going to be both odds. Okay. So that's kind of the basic idea of like finding some probabilities. But let's talk about some of these properties, some of the principles of probability. So first off, while doing these examples, you might have noticed that all of our answers were less than 1 and positive. That's not coincidence, not random chance. It's a rule. The rule is that probability of something is between 0 and 1, inclusive. It's possible to have 0 and 1 be the probability, but that's the rule. You can't have less than 0, which means no negatives, and you can't have more than 1. You can't have 150% chance of something happening. That doesn't work. The best you can do is 100% or 1. Probability event that cannot occur is 0. So 0 is something that's impossible. So you roll that 6-sided die and you get a 12. Well, there's no 12 on a 6-sided die. That's impossible. Call that an impossible event. So it's something that can't happen. That's an impossible event. Probability event that must occur, so something that's going to happen, it's guaranteed, is going to be 1. So that 1 tells us it's going to happen. There's no ifs, ands, or buts. It's going to happen. We call that certain. So an example like that would be I roll that six-sided die, and I get a number smaller than 7. Well, since the only numbers on that die, 1 through 6, are all smaller than 7, then they would have to happen. That's guaranteed. So the numbers, probabilities are going to be between 0 and 1. It might be 0 if it's impossible, can't happen. It might be 1 if it's certain, if it's guaranteed to happen. So let's look at some examples and determine, if it's between 0, 1, 0, 1. If you roll a fair six-sided die and get a number less than 10, well, six-sided die, that's 1 through 6, right? Since we want something less than 10, well, all the numbers less than 10, so this one's going to be 1 or 100%, right? This is the chances. All 6 sides out of the 6 sides possible, right? If you do good options, all 6 of them are good because they're less than 10 out of the 6 possible, so 6 over 6 gives me 1. So again, because it's certain, it's 100% chance, or it's a 1. It's got to happen. We draw a card from a deck and get 6.5 of spades. Well, there's no decimals or fractions in decks of cards. They have just whole numbers. So this is not possible. So this would be 0 or 0% chance. This is impossible. So if you think about it, how many good options are there? Well, there's no 6.5, so there's 0 good options out of the 52 decks of cards in a regular deck. Since there's no good options, 0 divided by 52 is 0, because 0 divided by anything is always 0. This one's 0 or 0% can't happen. It's impossible. Now, like we said, all probabilities have to be positive. They have to be between 0 and 1. Maybe it could be 0, maybe it could be 1, but that's the rule. So which ones could be probabilities? If I give you these numbers, which ones could be? Well, 0.4, that's fine, right? Because 0.4, that is between 0 and 1. It's bigger than 0, less than 1. 1/2, definitely. That's the same as 0.5, and that's fine, so that works. 2 doesn't work. 2 is equivalent to having 200%. And we said that probabilities over 100% do not happen. Anything bigger than 1 does not work. So this is not possible. You can't have 2 as a probability. 11%, 11% is fine. That's the same thing as having 0.11. That would be a decimal, between 0 and 1. This works fine. That's good. 5/3, you could never have the top of your fraction be bigger. This is the same thing as 1 and 2/3, which is bigger than 1, right? That's too big, so this does not work. So we can't have 5/3. The fraction on the bottom should always be the bigger part, the bottom part of the fraction. And that makes sense because we said the total is on bottom. The total should be everything, so the bottom should be bigger. Okay. Let's talk about some definitions, some terms we're going to use throughout the rest of this chapter. First one is events and outcomes. So in probability, we refer to each possible result as an outcome. So every different result you could get. So when I'm looking at that die, I can say when I roll a 1, that's an outcome. It's one of the outcomes. Rolling a 2, rolling a 3, rolling a 4, those are all outcomes. We use the word event to refer to a collection of outcomes. So events are collections of outcomes. And usually when we're finding the probability, instead of finding the probability of a specific outcome, we usually try and find the probability of an event. Like when we said the probability of getting even on the side of the die, that's a collection of different outcomes. All of them that are evens. So for example, when rolling a die, the event could be rolling an odd, so that could be an event. Rolling a 4, and that one is an outcome, but you can have an event that's limited to just one outcome. That's allowed. Typically, they're going to have more than one thing, but not always. Rolling a number less than 5, like 1, 2, 3, 4, those will all be part of that one. Those will all be events. So events can be multiple outcomes. They can be a single outcome. Usually they have some kind of property they all share, like being odd, being less than 5, being 4. Then there's only one thing that shares that. There's only one 4 on a 6-sided die, but those are all different events. Let's look at an example here using the hair color charts. You probably did these back in science class in grade school. So my wife and I both have brown and blonde alleles, the genes that give you your hair color. Our baby's going to receive one hair color. I think I wrote this question back when our son was going to be born, and now he's 4, so this question is getting a little bit old. That happens, but yeah. So his hair color is going to come from his parents. Each one of us is going to contribute some of these genes. So we want to look at the possible outcomes for the baby. What's the probability of getting a brown? So for this, looking at the probability, well, since we both have 2 genes to share, we have to think about that option. So he has a brown blonde from his mom and a brown blonde from his dad. And so the probabilities or possibilities, the possible outcomes, he could have a brown brown. He could have a brown blonde. You could have a blonde brown. And you could have a blonde blonde. So those would be the different possible combinations. So these would be the outcomes, the different outcomes. So these would be outcomes that would be possible for this. So each one of those would be a different outcome. Now, what is the probability of getting a brown brown? Well, there's only one brown brown, so the good options, there's only one of them, brown brown. Over the total, well, there's 4 total outcomes. So there's a 1 in 4 chance that they're both brown. Pretty sure you probably got the brown blonde. Actually, I think it's actually more complicated. That's when you study more science and find out there's a lot more to it than just the one gene. But that's the idea. And I think they have you do this little chart in the homework, so I want to make sure I did one of the notes. Okay, let's talk about a simple event. So a simple event, this is a specific type of event that cannot be further broken down. So you can't break it into simpler parts. You can't go any less. So a simple event cannot be further broken down. That's what makes it simple. So for example, rolling a 5 on a die is a simple event because there's only one option, a 5. Rolling an even is not, because even you could break into 2, 4, and 6. Those are all even. Those would be separate events. So there's 3 different ways you could break that down. So again, something that's so simple you just can't break it down any further. The sample space, so the sample space is where you want to know, is the collection of all possible simple events. All stuff that can't be broken down any further. So that would be your sample space. Sample space, all the simple events. Okay. So if a couple has triplets, what would the sample space be for the possible genders? So we're looking at sample space for possible genders. We're looking at boy, girl, keep it simple. So if they have triplets, what could happen? Well, options are they could have all boys, right? That's one option. Another option would be they have one boy and 2 girls. Another option, they could have 2 boys and 1 girl. And the last option, they could have all girls. Since we're looking at what the possibilities are with genders, these would be our 4 different events. These would be the 4 different events that we could have here. You can't really break it down any further because we're looking at just the gendered, right? We're looking at, okay, they're all the same, all boys, all girls, 1 boy, 2 girls, 2 boys, 1 girl. You can't break that down any further. So this is the sample space. These are the different possible events. And then let's look at what the results are. So for all boys, that would be when you have boy, boy, boy. So there's only one outcome that fits in that set. 1 boy, 2 girls. There's actually a couple options here. You could have boy, girl, girl, or you could have girl, boy, girl. Because of course, when you have babies, order happens, right? So you can have the first one be a boy, but then the second 2 are girls, or the first one's girl, and then a boy and then a girl. And then of course you could have girl, girl, boy. And those would be 3 different outcomes that would fall in this sample space. But you really can't break this down any further. You can't, break it down more than 1 boy and 2 girls. So this is still a simple space, even though it has more than one outcome, because there's no way to kind of break this down just simpler, more parts. Next one, 2 boys and 1 girl. So it'd be like having boy, boy, girl, or we could have boy, girl, boy, or girl, boy, boy. And again, that one would have 3. And then all girls, there's only one option, which is girl, girl, girl. So now what would be an event that's not simple? So that was a simple, all these are simple. Based on that idea, what's an event that's not simple event? So one example from this is having all same gender. Because that you could break up, right? We could have all same gender, or we could have all boys, all girls. And that could be broken up into those 2. You could have 2 same gender. So then we could break it down between 2 girls or 2 boys. And so that could be broken down. So these would be things that you could break up into simpler spaces. Not all same gender. So that would be another one you can break down, not all same gender. Because then you can break it into the 1 boy, 2 girls, and 2 boy, 1 girls. So these would be all things you could break up. versus these would be simple spaces. You can't really break down anymore. Okay. And we're almost done. This is a short section because we're really just getting into probability. So last page here, I'll talk a little bit about the notation. So when you talk about probability, we use the word probability a bunch. It gets to be really annoying to sit there and write probability of something over and over and over again. So to make it easy to talk about, easy to write, we're going to use capital letters to refer to events. So when you see me talk about using capital letters in this section, we'll use capital letters referring to event. So event A might be getting an even on my dice. Event A might be, all the kids having the same gender in a family. Event A is just what we're looking for, that collection of outcomes. And then we'll use the notation P of A. And this denotes the probability of that event A. So P of A, when you look at this, don't think multiplication. We're not doing multiplication, we're doing probability right now. We'll do multiplication with probability later. But for now, this P of A means probability of event A. That's what that means. So if I do like probability of an even, that means the probability. I spelled probability wrong. Whoops. Probability of event getting an even. And you can see why we'd rather write this instead of writing all that. Writing this whole sentence out versus just putting P in parentheses even. So whatever's in the parentheses, that's what you're trying to get. And the P in front of it just means we're looking for the probability of getting that. We're not trying to find out, what the options are. We're looking at what's the probability? What are the chances of getting whatever's in the parentheses? Another thing we'll deal with probability is complementary. So I'm going to just make sure we mention this. So complementary events. The word complement has to do with what goes with something, so it's not the same but goes with. So complementary in probability refers to the event not occurring. So it does not. The big thing here is it's not going to happen. So that is the complement. We write it as a complement with this bar above. You might call it a bar, but I think I usually call it a complement. So that is A does not occur, the complement. So A complement, so if we do like probability of A complement, that means probability A does not happen. So instead of looking for A to happen, we're looking for everything else. So instead of the thing we typically call good is A, we're going to say everything else that's not A would be the good stuff, the stuff we put on top. So for example, if A equals rolling a 4, so it's a rolling a 4, that's what A is. What is A complement? Well, A complement is going to be not rolling a 4, right? So we're not going to get a 4. So if it's a 6-sided die, this is going to be, the set of things. It's going to be like 1, 3, 5, or 2. Why did I skip 2? And 6, right? So everything that's not a 4. Order doesn't matter. It's okay. Everything that's not a 4. That would be your set of things that would be a complement. That's the things we want. So what's the probability of getting A? The probability of getting A, rolling a 4, well, there's only one of them, right? There's only one 4 out of the 6 sides of a 6-sided die. So 1 out of 6, that's probability of getting A. Probability of not getting A, well, there's 1, 2, 3, 4, 5. There's 5 sides that are not A out of the 6 sides. The probability of not A is 5, 6. Notice that 1, 6 and 5, 6, you put them together, you get 6, 6, or you get the whole, 100%, everything. And that should be true. If you're doing it right, if you're doing probability of A and A complement, if you're looking at complement correctly, then the probability of those two things together should always give you everything, right? Because you're breaking it into two distinct sets. The stuff that is A and the stuff that's not A. So if you break it up like that, you should always have two parts that put together give you the whole thing. So yeah, that's probability of not A, that's probability of A. And again, not A is not getting a 4. Let's do one more. I'm going to try and draw a king from a standard deck of 52 cards. Note that there are 4 kings. Don't really worry too much about your cards. I've had students in the past that freak out because they're not big, playing cards people. On the tests and stuff, I'll try to be careful about, if I give you questions with cards and stuff, you'll see this in the homework and stuff too. they'll provide the deck of cards or the information about the deck of cards you need to know. You don't have to really be like freaked out that you're not a huge playing cards person. So don't worry about that too much. You'll kind of see that as you go through the homework quizzes. They're just nice for examples. So that's why I tend to use them for examples. Okay. So event B is drawing a king. So B is drawing a king. There are 4 kings. So there's 4 good options here. The king of hearts, king of spades, king of clubs, king of diamonds. What is B complement? Well, B complement, not B, is not drawing a king. So that's going to be drawing anything else, right? So that's going to be, jacks, queens, aces, 2 through 10. All that stuff is going to be stuff that's not a king. So all that stuff's going to be in the complement. Okay, well, what's the probability of getting a king? So what's the probability of drawing that king? Probability of drawing a king, well, there's 4 kings, we said, out of 52 cards. That does simplify. You can divide both top and bottom by 4, so you get 1 out of 13. So 1 out of every 13 cards is a king. Now, if I want to do probability of not getting a king, well, there's 2 ways to do this now, because now we notice from the first one, the 2 probabilities should add up to give you a whole. So you could just take 4 out of 52 and figure out what the rest is and say that's 48. Or you can think about all the cards here. You can think about there's 4 jacks, 4 queens, 4 aces, 4 2s, 3s, 4s, 5s, 6s, 7s, all the way through 10. And if you do that, you end up with 48 cards because there's 12 different numbers here, 4 times each. So either way, you end up with 48 out of 52 because yes, these 2 should combine to give you the whole set, right? 4 out of 52 plus 48 out of 52 should give you the whole set, 52 out of 52. So that should always happen when you're doing something that's complement. You should add it to be the whole thing. This one does also simplify. You can divide both the top and bottom by 4. So you get, 12 out of 13. You can see they still are complements. They still match up to give you the whole set if you add them now. And that's the introduction to probability. So we're just getting started. I think we have about 4 sections here we're going to cover in probability. So we'll get further in. We'll kind of develop more ideas. But that's a big idea. Probability is probably one of the biggest sections we're going to cover on this first exam. So the last section we did was chapter 3, where we're dealing with measures of center, measures of variation, relative standing, so mean, median, modes, z-scores, all that kind of stuff. That and then this section, probability, are going to be like the majority of the exams. The first exam, you really want to be ready for chapter 3, 4. We're not going to put a lot of chapter 1 on there, like we said, because it was mostly just definitions. But we will see a lot of chapter 3 and 4, so you ought to be ready for these chapters. All right, that's it for today. So I'll see you on the next one.